if you remember from, again, physics 1, when we used to say if you have a net force equal to 0, that means no external forces, we have conservation of linear momentum, which means what? The linear momentum before equals the linear momentum after. Well, here in this chapter we're dealing with angular momentum, things that's spinning. So if the net torque is 0, then we have conservation of angular momentum. Which means the final momentum, we use L for angular, should equal the initial momentum. You'll notice that actually, you'll see the where this logic is being used when a diver dives off a diving board. And if they want to spin, what do you notice what they do? They bring their knees back close to their chest. They make their body smaller. And what they do, they spin. You see that in gymnastic. You see that in ice skating. When, especially the ice skaters, when they want to spin fast, what do? They bring their arms close to their chest. Yep. And you see them spinning much, much faster. They want to slow down. They open their arms, they open their legs, and they slow down. That goes to the logic of conservation of angular, that L always gets me confused. Conservation of angular momentum. The momentum before equals the momentum after. Again, if the net torque acting on that is 0. We can do this demonstration actually. We can have somebody sit on a chair and spin them and have their arms stick out there and watch that person bring their arms close to their body, and you'll see they start to spin a little bit faster.
You ready?
No, I fell off it one time. I got dizzy. I said, that's it. So let's take an example. Let's say we're going to take a person and have that person actually sit on a chair as the person, arms wide open, as the arms open like this. And let's give you some numbers for this person. Maybe it could be holding some weight in their hand to make sure, because as you put weight in their hand there, you just change their inertia by a lot actually, because especially if they're holding a decent amount of weight. Because the inertia is what? mr squared will be the mass of that weight times that distance, the length of the arm squared. And the same thing for that one. So they're sitting on the chair, we're spinning the chairs around, and they're spinning around their center right there. They're spinning around this line here. You're spinning around the center of your body there. Let's assume the angular speed for that W is 3.74. And this person has inertia equals 5.33 kilogram times meter squared. And what's going to happen, we're going to spin the person, we're going to ask the person now to pull their hand close to their body, so the weight is right there. What that does, because you bring in, just think about it, your body itself didn't change. Your inertia really didn't change by much. It reduced because your hands moved in now closer, the distance smaller. But the weight you're holding now is sitting right there in the center of the rotation, the axis of rotation. It has no inertia. So the inertia will drop here. That's why what will happen is your inertia becomes much, much smaller. And we'll use, for example, 1.60 kilogram meter squared for it. That's what's going to happen. And the question, can you tell me what W for this person now? How fast is he going to spin? Well, we know inertia is equal to I times W. So the final inertia, I times, we'll use the final inertia times W final should equal the initial inertia times W initial. This is the final inertia when you bring your arm closer. This is the before. So the final inertia is 1.60. W final. The initial inertia is 5.33. W0, which is what? 3.74. And the only unknown that you see there is WF, the final angular speed, which is 5.33 times 3.74 divided by 1.60. .46. You're spinning a lot faster now. Much, much faster. The unit for that is rad per second. That's W. What are you yelling, Rich? Let's try another one. Let's take stars. An object here. We have a star. Big star here. It has a radius R equals. Excuse me. Thank you. Excuse me. 2.3 times 10 to the 8 meter. So it's not a small star. Oh. The mass is going to be big there too. And it's spinning there. It has a W of 2.4 times 10 to the negative 6. It's not spinning that fast. Rad per second. Barely turning. Let's assume the star is going to collapse. You probably seen or heard about stars collapsing. When they collapse, the size shrinks. Smaller now. The radius now, let's use what? Probably going to be about 2 times 10 to the 4th, let's say, meters. Shrunk by a lot. And again, we need to know what is the speed, the angular speed of the star. What's W? This is the initial, this is the final. Find final angular speed. We say, well, we have conservation of, I'm going to leave a space, but we have a conservation of angular momentum, which means LF equals LO. LF is IF, and here's my problem. What is I sub F? LO is what? I sub O times WO. I don't know what I's are. Do you know what I is? Well, what is the shape of a star? When you think of a star, what does it look like, the star? Doesn't it look like a basketball? Like, think of the Earth. The Earth shape looks like a basketball. The Earth spins on its what? On its axes. If you look at the Earth, the shape of the Earth, it looks something like this. In 3 dimension. And we have an axis that the Earth spins around that axis. So it spins around the center of the Earth, that line there. It's constantly spinning there. So let's see what the inertia for that is. Where's your book? Inertia for a sphere that spins as a solid sphere, not a hollow. Notice the Earth, if you dig in it, there's dirt under. It's not just a shell. It goes all the way to the core. It's a solid sphere The equation for inertia for a sphere is what? 2/3 mr squared. I mean 2/5. 2/5 mr squared. So the inertia for a sphere is 2/5 mr squared. But we have a little problem. What do you notice? I never gave you the mass. That's still okay. What's the initial inertia? It's 2/5. We don't know what the mass is. Leave it as m times r squared. R is what? 2.3 times 10 to the 8. Oh, it says 108 instead of 10 to the 8th. I hate this eraser for this one. There we go. 10 to the 8th squared. And what is the final inertia? It's 2/5. The mass didn't change. What happened? Everything just sunk in there. Nothing left. And this is 2.0 times 10 to the 4th squared. Now plug them in. Final inertia, that's 2/5 m times 2.0 times 10 to the 4th squared times W final equals the initial inertia, which is what? 2/5 m times 2.3 times 10 to the 8th squared times initial W0, which is what? 2.4 times 10 to the power of -6. Now, if you look at that, you'll notice 2/5 m in both sides, so you can just drop them out. Can you calculate what WF is? This times this divided by that number. This times this over this number. So let's see what that number is. Clear. 2.3 e to the power of 8 squared times 2.4 e to the power of -6 divided by 2.0 e to the power of 4 squared. I came up with 317.4 rad per second, spinning really, really fast. If you want to know how fast the Earth, now that star is spinning, divide that by 2 pi. And that will tell you how many revolutions per second. It's doing roughly 50.5 turns every second. Per second. So if you were on that planet, on that star, you definitely will be dizzy. 50 spins every second. By the time you go 1 Mississippi, you just spun 50 times, 51 times. This, by the way, is the logic that creates tornado for us. When you look at a tornado, it says touches down. Or the hurricane, when you look at the eye, the center of the hurricane. In the center, the thing moving a lot faster there. Because the radius shrunk. The outside, when you have a big cloud there, it's moving. It's not moving that fast there because the radius is big. But when you shrink it to that little 1-2 feet tunnel there, that's going to be spinning at high speed, and that's why they pick up your house like nothing. You know, that wind becomes 150, 160 miles per hour. Deerfield yesterday got wind up to 90 miles per hour, I guess, last night. Deerfield, Mass. I don't know if it was something going on. I didn't even hear anything last night. Let's try another one, another example here. Um, this number, by the way, if you do the math, that's equivalent to about 3,000 RPM, approximately. Just to give you a heads up, so you're really spinning on that one, you know. Let's take another one. We'll do, what story we're going to use? An ice skater? Okay. We have an ice skater here. There's the skates on their feet. There's a young lady. She's skating. Her arms are there. Inertia's I. She pulls her arm close to her body. And by doing that, here's the skate again. The arm's right here. Your inertia becomes half of the initial inertia, usually, around that, in that neighborhood. By bringing your arm closer to your body, you always tighten your body. You can always lower your inertia to half where it used to be. My first question, what is the relationship of her final angular speed to the initial angular speed, or the initial to the final? Is the final speed going to be double? Is it going to be tripled? What is it going to be? And while we add it, or it stays the same, how about the kinetic energy? Is the kinetic energy, as question number one, is the initial kinetic energy equal to, question mark here, to the final kinetic energy? Or what's going to happen there? Is it bigger? If it's bigger, is it double because this is half the size? I don't know. Let's see what will happen. Again, there's no outside forces on that. There's no outside net torque. So conservation of linear angular momentum. The final angular momentum. Inertia final times W final. Initial one, I initial times W initial. I didn't give you any numbers intentionally. All I said to you, the final inertia will be half the initial one. So this is 1/2 I sub O times W final equals the initial one times what? W initial. Notice both of these have I-O in them, so mathematically I can just drop them out. I have 1/2 W final equals W initial, or W final is going to be twice the initial speed. So when you shrink the inertia to half the size, what it used to be, you're going to spin twice as fast. So if you were spinning at 8 RPM, you're going to be spinning at 16. If you were spinning at 10 RPM, you're going to spin now at 20. Twice that number. What about the kinetic energy? Let's look at the kinetic energy. We're talking about rotational kinetic energy. Kinetic energy due to rotation, the initial one. 1/2 I W squared. That's the equation for it. So the initial one is going to be 1/2. Inertia is I sub 0. And W is W0, and you square it. Which is and what is the kinetic energy, the final kinetic energy due to rotation? It's 1/2 Your initial inertia. Wait a minute. What is your initial inertia? I mean your final inertia, I'm sorry. What's your final inertia? I final, W final squared. 1/2. The final inertia is 1/2 the initial. And W final is what? Twice the initial squared. This will give me a 4, this will give me 1/4. The 4s will cancel. That's what the final kinetic energy will be. If you look at that number, isn't that twice the initial one? This is half of this, which means this is twice of that. So the final kinetic energy is twice the initial kinetic energy. You have more kinetic energy. One of the topics or one of the labs we're going to be doing this week, if it's not today, tomorrow, I got 2 labs in mind for this topic. One of the labs is actually we have a plate, and you'll see it's sitting on this platform that spins really easily. You take your finger and you spin it, and it will be spinning fast. Then we have a heavy weight that looks like a ring. You grab it and you drop it on top of that where it lands on top of it. And what you're going to notice, the minute it lands on top of it, it doesn't move, it sticks to it. But what will happen to the speed of this? It becomes much, much slower. Why? We just changed the inertia for that. Because if you look at it, let's say the 2 plates, each one, just to, I'll go through the math. This is a solid disc, a disc here. And let's say it has a mass of 5 kilograms, it's not a small one. And I can tell you the radius for them, where's my ruler? Because I have to eyeball it to see. I know what it looks like. The radius for it, the device we use in the lab probably has a diameter of probably 20 centimeters. So the radius will say 10 centimeters. It's solid. You'll see. There's no hole in it. Spins. So after that, what we do, we take that device while spinning, still the same piece here, and now we drop, I don't know if I can draw that, on top of that, we drop a ring, a loop there. That's 3D here. We have a ring that we drop on top of it. So the bottom piece, still a disc, the bottom one, that's still a disc with mass equals 5 kilogram and radius equals 10 centimeters. But the loop that we drop, the hoop that we drop on top of it, it's also heavy. We'll say it has a mass. I'll give it 7 kilogram and the same radius, the same size. That just sits perfect on top of it if you drop it. And let's assume this was spinning at the rate of W equals 10 rad per second. The question is, what is W going to be here? This topic, we call that rotational collision there. Things are spinning, but they're colliding there. That's what we call that. No coffee there. Ruler here. So So let's look at the before. What was the inertia before? That's a solid disk. Again, I got to remember to give you guys this handout with the inertia. For a solid disk, 1/2 mr squared. So in this case, it will be 1/2. The mass is 5. R is 0.1 and square it. .5 times 5 times 0.1 squared. And we got 0.025. What about the inertia after? This is the initial one. The final inertia is going to be the inertia of the disk, which is what? Still 0.025. The bottom piece didn't change. But now we added to that little hoop, that ring on top of it. It's just a ring, not a solid one. And the inertia for the ring, it's mr squared. When it's a ring. When you have a hoop, the inertia for the hoop is mr squared. We're talking about the m for the red one. So the blue one is the bottom one, plus the inertia for that hoop on the top, which is what? 7 times 0.1 squared. And the result becomes what? 0.095. Again, final angular momentum equals initial angular momentum. I final, W final equals I initial, W initial. I final 0.095, W final, I initial 0.025, W initial was 10. Can we get what the final speed is? 0.025 times 0.1. Oh, that's 10, not 0.1. Divided by 0.095. Notice the speed becomes 2.63 rad per second. Much, much slower. The heavier the object, the slower it's going to move. The lighter the object, the faster it's going to move. It will never be faster than the 10 rad. The only way to be faster than the 10 rad, if you throw it on an angle, or to push it. But if you just drop it straight down, because if I come and throw it on an angle, like the next example, I'll do one that way. I could increase the speed even when you have collision there. This one we reduce the speed. The next one you'll see I'm going to increase. Well, maybe not. I might not increase it. It will increase it actually. The way I'm going to set it up. Here's the last one on this. I'll take a merry-go-round, big merry-go-round, at rest. It has a mass of what? 512 kilogram. So it's not a small one. Well, actually, that's not the mass, that's the inertia. We can calculate if they give us that, but they already calculated that. They give us the inertia actually, 512, which is mass times 1/2 mr squared, because that's a solid disk, the merry-go-round. But that was calculated for us, so the inertia is 512 kilogram meter squared. They did the math for us. Has a radius r of 2.31. So I could tell you how heavy that merry-go-round actually. If I want to work it backward, this is a solid disk. If you've been on a merry-go-round, you know it's a platform. It's solid. It's not a hollow one. You can walk on it. So it's a solid disk. 1/2 mr squared. That's what the inertia. Since you know that number, you know r, you can find the mass. Now this is now moving, W is 0. Now we get a little brat, a little boy, comes running this way, tangential to that. So there's a boy that has a mass of 34 kilogram running and jumps on the merry-go-round on the edge of that. When he was running, has a speed of 2.8 meters per second, or velocity is 2.8 meters per second. And he jumps on the merry-go-round. What's going to happen to that merry-go-round? Here we go. And there's the person now sitting here at the edge of it. I put him at the edge. This is going to start to move. The question is, what is W now? So that's what we have. Now, let's find that this is the initial, that's the final. We'll call this F. The initial equals the final angular momentum. The initial is the initial for the merry-go-round, mg, plus the initial for the child. The final is L for the combine, because the boy is stuck on it with the merry-go-round. So let's look at the merry-go-round. The angular momentum is what? Inertia times W, right? For the child, well, remember we said the inertia is, angular momentum is what? I times W. We also modified that. We said what? R times M times V. Look at the notes. Somewhere last class, we derived that equation. I can tell you what section. That was section angular momentum, section 11.6. In case you wonder where it came from, it will take me 2 seconds to derive it. Here we go. L equals I times W. I usually summation of mr squared. That's what I is. And W is what? V over R. If you do the math, what do you have? M times R times V. That's where it came from. Equals the final times W final. Here we have no idea what the inertia, we do with the inertia, 512 for the merry-go-round. Initially not moving, that's 0, plus, now the person, the mass of the person, which is 34, running at a speed of 2.8, and I made the person land at the edge, so what is R equal to? 2.31? Because he landed on the edge. See why I drew him? If I put him on the inside, it will actually have less, will move slower. And now we need to find what the new inertia is. Now the child is sitting on that. The new inertia is going to be whatever the old inertia, which is what? 512 plus Add to it the inertia of the person, which is mr squared. The mass of the person, which is what? 34 times r, which is 2.31 squared. Inertia is mr squared. Unless you want those special pieces, like the hoop, which is, or the sphere, 2/5 and all that. But inertia is a summation of m times r squared. We know what the mass of the person, we know what r is. Can we find what Wf is? So let's see what do we have. This is 0. 34 times 2.8 times 2.31. Oh, I forgot to turn on. That will help. 34 times 2.8 times 2.31. 220 roughly. Let's find what that number is. 2.31 squared times the 34 plus the 512. The inertia now is 693.4. What is Wf equal to? 220 divided by that number, which is 0.317 rad per second. So by that person jumping on it is going to change the inertia too. The inertia is whatever the inertia used to be, plus add to it the inertia of that person, which is the mass times r squared. So in this case, we actually increased the speed. We went from 0 speed to a final speed of 0.3. In the previous one, we dropped it straight down. So we never had to add this piece to it because there was nothing moving. I just dropped it down on top of it. So the piece I dropped in this example, it really didn't have any initial angular momentum, nothing. So it just increases the inertia, which made it go a little bit slower.